Hello, my name is Kyle. Coming here on behalf of Perfectly Soft to talk to you guys about server-side Swift in general and a little bit about Perfect in particular. I've come from sunny and warm Canada, and I'm very happy to be with you today. So first off, what do I mean when I talk about server-side Swift? Primarily, this is Swift that's running on Linux. It doesn't have to be on Linux. You can also, of course, run it on your Mac, and you'll find a lot of companies who might have a lot of Mac minis laying around are perfectly happy and willing to deploy their own servers locally. And it applies to this as well. But primarily, we're talking about Swift running on Linux. And again, this could be either located on a physical computer in your office. It can be on any cloud provider or a physical computer that's co-located in some sort of service provider. And of course, it is a server. It's responding to network clients, accepting requests and formulating a response and spinning it back to the client. So these processes that we're talking about are anything from simple API servers, complex API servers, workers, processes that run and maybe look for certain events and then process them and either return a response or maybe pass the task down to another service that's running. And of course, websites, which when you talk about a server, that's what many servers are these days, are serving web pages. And a lot of services, a lot of applications combine a variety of these together to make the entire infrastructure for whatever sort of enterprise that you're trying to accomplish. And of course, part of this is iOS or Android backends, and this goes back to serving API requests. So you have your iOS or Android device or whatever sort of device. They know where the server is, they connect to it, send data, get a response. We'll go into more detail on that. And in addition, Swift on the server could be part of a peer-to-peer system where the client and the server are both operating together. You might consider maybe a video chat service where you have multiple clients, multiple essentially servers, and they're all on the same device. And you have a lot of people making peer-to-peer connections. So you can use Swift in that regard as well. So why Swift on the server? We all know that Swift performs pretty well compared to a lot of dynamic languages. And so performance is one of the biggest reasons why you might want to run Swift on the server. And it does get a lot of this performance because it is a statically compiled language. And what static compilation does, it really shifts a lot of the work in determining what particular objects can do. Shifts that to compile time, so it's done once ahead of time, and you as the developer get the privilege of waiting for that to build. But then once that's done, you never have to do it again. So then you have a very fast language that's done as much of the work that compile time as it possibly can. And this is work that dynamic languages do at runtime. And that's part of the reason why Swift can be so much more performant than more dynamic language, for example, Ruby, Python, things like that, which are commonly used on the server. Swift also has very strong type checking, and what this allows you to do is take care of many errors at compilation time, and these are errors that you don't have to see at runtime. And then this really translates to fewer surprises on the server at runtime, which is that nobody wants to be woken up in the middle of the night because their server got a little crash. And Swift really facilitates this, discovering the problems early, letting you take care of them quickly before anybody else sees them. My next point here is that Swift is better for maintainable systems because it has this strong type checking. And I put a question mark there because Swift is a very young language. It's going through a lot of changes, but the impacts of these changes are getting much better. I believe there were only a few issues that we had to account for moving from Swift 3.02 to Swift 3.1. And so as Swift ages, it gets better and better in that regard. There are fewer things that break as you put out, as Apple releases a new version, or rather Swift.org. And this is the same problem that any iOS or macOS developers have when using Swift. The version changes, you have to do the convert your syntax and blah, 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 and take care of all that stuff every time. But like I said, it's getting better and better. Hopefully, shortly in the future, Swift will let you build more maintainable systems for the server. So one of the reasons why you would want to use Swift on the server also is because it lets you share a common language for the client and the server. And this is important for people who are working on iOS apps, Mac apps, and they also have a server that they need to go along in the system. Using the same language on the server and the client lets you share code. For example, you could share sharing code on the server and the client. So you can use the same base classes on Swift and provide extensions on the client and provide extensions on the server which expand on these base objects. For example, you might have a user object which has a first name and a last name, and there's some common behavior there about validating their name, their email address, making sure things are formatted properly. And if you're using Swift on the server and on the client, you can standardize these functions into one set, and they're shared. If they change on the client, change on the server at the same time. And you can provide extensions which are specific to the server, and extensions which are specific to the client. For example, the client might change someone's first name or change their email address, and they might call a save function, and the save function will send it to the server. On the server side, it might have the same process. So you have a save function, but instead of sending it off to be saved, it might put it in the database, which runs there on the server. The other benefit for using Swift on the client and server is that you can standardize your development teams to a specific language. Instead of having to use, say, JavaScript, Ruby, Python, and Swift to pull together your multi-component system, servers and clients, you standardize on one language, which I think will ultimately is a pretty decent one. So you really leverage all your existing knowledge when you move to writing server-side software. Well, one of the benefits here also is you get simplified client-server debugging initially. And the reason you get this is because, again, it's all in one language. You're using one IDE for developing both of these components. So you can easily have multiple targets in your project, and you can start up the client, start up the server, and handle the development and the debugging of these systems that are talking to each other right in the same IDE, which is very nice. Another reason which maybe a lot of people might not consider as being too important, but we found it as being quite vital in what we try to accomplish here. C has a very good, or Swift has very good C bridging, and this means that you can import existing libraries, drivers, software written by other people in C, and very easily bridge that into Swift and take advantage of that functionality. Usually you don't have to write C yourself. Sometimes it can be helpful if you need to do some optimizations, but for the most part, if you're going to use an existing third-party C library, you can import it all from within Swift using the nice unsafe functions and objects. And We'll go into more of some of the projects that we have in our GitHub repository, but many of them wrap existing C libraries. It's been very important for bringing in database connectivity and things like that. Why would you not want to use Swift on a server? Well, some of the drawbacks, I guess the biggest one is that it is a young language. And usually server developers, good ones, I think, are a bit conservative. You want to make sure that the code you have running on the server is going to be stable and that you're going to be able to maintain as you go into the future. And as we know, Swift is a pretty young language. I believe it's coming up on 2 years when Swift was announced as an open source, I believe at WWDC. It's at that point that we started working on Perfect. Another disadvantage is because it's a young language, there aren't a lot, there isn't a lot of history of questions and answers on, say, Stack Overflow and these sorts of services. And when there are, you often find that the code snippets or whatever was posted is now out of date, and again, that goes back to how rapidly Swift is evolving. So there are fewer third-party contributions, and the ones that you do find, again, it's kind of hit and miss as to whether or not they build with the latest tool chain. And sometimes, if you try and update it, sometimes it goes well, sometimes it takes a lot of time, and it's just not worth it. But as time progresses, as Swift stabilizes a little more, particularly I think after version 4.0, a lot of this will fade into history. Another reason why you might not want to use Swift on a server is it corresponds to one of the reasons why you might want to, and that is because it is statically compiled. There's a lot more work to do to get something running. In a lot of the dynamic languages that people use for servers, getting the code up there is as simple as just moving the text file. Of course, with Swift, it's not a scripting language. It is compiled ahead of time. So there's a little bit more work. It's a little bit less flexible. But that's all part of a trade-off, which gives you better performance. So if you're doing rapid prototyping or trying to quickly get a system up, you might find it easier to use, one of the more traditional server languages, PHP, perhaps, Ruby, something like that. So that's just a trade-off, and it's something to think about when you're moving forward on a system, whether you want to embrace kind of a rapid prototyping philosophy, or whether you want to make it more of what you might call an engineering effort to come up with a nice workable system. What does Swift on the server look like? Most people are already familiar a little bit with how clients and servers work. We all have a good deal of knowledge about how to use the internet. None of us would be here, I don't think. So what we're talking about here are many, many clients, hundreds, thousands, down to even just a couple. And these are browsers, mobile apps, devices, what have you, your car. And usually one or more servers. And this is all becomes kind of magic as far as the clients are concerned. They could be talking to a different server every time they do a request. But it's all hidden behind load balancers or some other sort of similar system that accounts for redundancy. In addition to your clients, your servers, which is your load balancer, almost every online service is going to need some sort of database. So we're looking at things like Postgres, MySQL, Mongo. In addition, you have software which acts like a database but provides a little bit of different functionality, caches in particular, things like you might use a software such as Redis for that, or Memcached. And it just enables you to, instead of having to go and get the database every time you do a request, You might look at the cache first and could provide a little bit quicker access. So all these components kind of go together to make what we're talking about on a server in particular, but server-side Swift in general. What is the workflow? The workflow is going to be a little bit different than what you're used to if you're an iOS or a macOS developer. The primary reason why it's different is because the Swift Package Manager. And that's really the method for macOS and on Linux for managing dependencies. So the Swift Package Manager is part of the Swift toolchain. As I mentioned, it's not used in iOS development, so if you're doing iOS development, you're probably familiar with CocoaPods or something like that. This is similar, but different. And it's a bit younger, it's still evolving pretty rapidly. But if you're going to do server-side Swift development, it's kind of the first thing that you need to get involved with. And it is a command line tool. It does not have any sort of UI components or configuration in Xcode at all. Swift Package Manager does generate Xcode projects, but at that point, the two they're acquainted, but they're really not close to each other. So Swift Package Manager works by using, it kind of uses convention over configuration. So at the core of every Swift Package Manager project, you have a package.swift file. And more or less what this does is let you list your dependencies. And here's a very, very small example of a package.swift file. It just has one dependency. And SPM dependencies are all fetched through Git. So that's what it uses, Git. There really aren't any other alternatives there. But it does use semantic version systems, so it relies on this. And these are all tags in your Git repository. Without these, Swift Package Manager won't work. And of course, you bump the version up, and when you're satisfied that you're ready to release this, you put the tag on the master branch, and that's just the way SPM works. Like I said, it uses convention over configuration, so it's a trade-off of flexibility versus just having things kind of work quickly. And so when you do specify dependencies, of course you can specify various specific versions, but you can also specify ranges. So I could say that I want to use a package, and anything from version 1.2 to version 2.0 is satisfiable for my project. So this goes more along with the conventions here. You have the package.swift file. Well, above that, you have your project, which sits in its own directory. You have the package.swift file. And within that, you have a sources directory and then a test directory. And SVN does let you, it recognizes your tests and it lets you run them. The tests look basically the same as what you would do in Xcode. There's another auxiliary file that deals with Linux specifics. And part of the reason why it has this extra file is because there's no Objective-C dynamic runtime on Linux, so it can't do a lot of the lookups for functions that the test runner on your Mac with Objective-C would do. But that's basically the only difference. It's a command line tool, like I said, it's a package manager. So there's basically two different classes of commands you run. You have the Swift package something, and then Swift build something. When you want to do just a regular build, Swift build. And if it hasn't fetched any of the dependencies already, it'll go ahead and do that. Download them, give you an error if it's version conflicts or connectivity problems. But there's a lot of other commands that you can run that you might do periodically through your development. For example, maybe you want to check and see if there are any newer versions for your software packages. Of course, a clean. Sometimes you always want to do a nice clean, and especially if you're seeing weird issues. And the other one here is the generate Xcode project, which does exactly what you would think it would do. It'll squirt out a new Xcode project for your Swift Package Manager project. It'll have all the dependencies in there. But due to the way it works with the version numbers on your dependencies, if you have one of those that gets updated, for example, maybe you run Swift Package update and you get a new version, your Xcode project is now broken. So in general, if you're using Swift Package Manager, yes, generate the Xcode project, use it, do your coding in Xcode, but don't edit the project. It's ephemeral. If anything changes, you're going to want to regenerate that. And if you have, there's a lot of settings that will get wiped out if you do that. So generally, the way we see development going, even though this software is intended to run ultimately on Linux, we believe that almost everybody who's going to be interested in Swift on the server are people running macOS and developing with Xcode. So the way we see the workflow is you're doing your coding and your initial testing on the Mac. You're using Swift Package Manager and Xcode. You're doing the development all in Xcode for the clients and the server. And note here that the Xcode workspace is very useful. I know in my workflow, if I'm working on an iOS app, I'll have the project file in a workspace, and then I'll also have the server in that workspace as well. And it makes it, again, very easy to just select which target you want to run, the client, the server, both of them, and you can monitor, debug their communications, all there using one piece of software, which is pretty nice. So eventually, you want to move things to Linux. The Swift builds are officially released for Ubuntu, and it supports 14, 15, and 16. Of course, there are other ports. People run it on CentOS, and a few other places, Raspberry Pis. But primarily what we're talking about here is Ubuntu. And generally you would run it locally through VMware, Parallels, Docker, which I'll talk more about, or through cloud. I mean, you can easily spin up an instance on AWS or something and just SSH into that and check your builds out there, see if things are running. But then, as you set it up, it's very important. One thing to watch out for is to just make sure that you're using the same toolchain version on the Mac and Linux. And the only reason that that's kind of a gotcha is because you do kind of have to get things installed twice. Install it. I'm sure we all have Xcode here, or perhaps something else. But here's another step. If you're going to want to run it on Linux, you've got to make sure you get that installed properly. Lots of nice instructions on the Swift.org site, and it's not too complicated to get there, or to get the toolchain installed on Linux properly. So yeah, after you've got your Linux, you've got your Ubuntu, you've got your code up there, you're doing your build, run, test sequence. Docker is very helpful for this, and we use Docker a lot in some of the software, which I'll discuss more in a bit. If you're not familiar with Docker, it's basically like a little mini Linux that you have there. Usually stateless. What you do is you build a Docker container, which is based on an image. So you have one image, and you can have multiple containers. The way I usually work when I'm doing Linux builds is I will mount my Mac folders in Docker. So as Swift Package Manager does its build in Docker, I end up with the binaries on my Mac. I don't have to go copy them out of it. It's done automatically for you. As we say, we expect most people are using Xcode, but of course you can code on Linux. If you're going to look at doing text editing on Linux, I would recommend Atom. There's a few plugins or extensions to Atom that to give you Swift syntax coloring, and I believe some people even have some sort of debugging LLDB in Atom, but I haven't played with that too much. Eventually, push it to the real server. And that is what we call deployment. There's quite a few options. Many here that we've listed, or according to Rocky, are services that you guys would have decent access to here. There's a few that you might not have decent access to. Access to Google Cloud can be a little sketchy from what I'm told. At Tencent, Alibaba, I do AWS, and Docker, again, anything that can run containers. And most of these services, in addition to giving you just regular virtual machines that you can SSH into and work with, they also let you push up Docker containers, so that's very handy. We have a system that does Google Cloud deployments, and that's exactly how that works. We use the Docker to do the build, and then through just another quick script that generates a Docker container that's ready to get squirted up there to Google. Heroku is another service which is quite popular, not so much for Swift historically, but it has many more constraints. Heroku does, so I'm not an expert on Heroku, but a lot of people like it. So, as I mentioned before, I'm here on behalf of Perfect, and it is a server-side Swift framework. So, what does that mean? The goal of a server-side Swift framework is just to make things far more simple. There's a huge amount of complexity in a server and handling requests and giving them responses, and our job and any server-side Swift developer's job or framework developer's job is to hide all that from you, just to make it as simple as possible. It's what you would expect if you're using, UIKit or something like that. You expect to get a lot of things for free and have a lot of decisions already made, and you just kind of fill in the blanks with your actual important code. So most server-side Swift framework, or most server system in general, whether Swift or not, works with a very simple model. Request, the app runs, and the response. So simple but complicated. The request comes in, your app code runs, the response is created and given back to the client. These frameworks should also handle server configuration. How many servers do you want? What ports are you going to listen to? Your SSH or TLS certificate, the path to that. Also handle, of course, TCP, very, very important. And then the multi-threading. You'll find, I think one of the bigger differences in a lot of the frameworks is how they go about handling concurrency and threading. And I'll talk a little bit about how we handle that. So here we have kind of the phases that one goes through as we're processing a request. And again, these are all things that the server-side framework is going to handle. So you've got the request parsing and what's called routing, which I'll talk about a little bit more, and then handlers. This is kind of the model we use. And that part is accepting the request and formulating the response. The server then does some work with what you generate to make a proper HTTP response, which can be sent back to the client. So what you'll see is a lot of facilities provided for parsing and creating JSON responses, encoding for HTML entities, parsing XML, and a lot of templating. That's taking a template, filling in the blanks for a custom response for the user. And two common examples of templating systems would be Mustache, and some people use Markdown as well. There's a lot of templating systems, and many frameworks include kind of their own custom system. We don't. We focus on Mustache, at least currently, and we did just recently introduce a Markdown system as well. So, Perfect. I consider Perfect a lightweight framework. I guess it's kind of opinion, it's not lightweight if it has exactly what you need. And if it has a little bit more than you need, then it's just getting ready for your future, I guess. What we do is focus on performance, and the core of Perfect is entirely async. And so what we try to accomplish here is a very scalable system that uses very few resources. And so Swift makes that pretty easy as long as you make the right decisions at the beginning. So that's really our focus, is kind of on performance. And you might say it's lightweight because it doesn't have a lot of systems that you have to get familiar with. We try to stick to a very simple model, and I'll show you some concrete examples in a second. So we are open source. Every one of our components are open source. We have, I don't even know how many repositories anymore. Billions, no, like 50 or something. And we are Apache 2.0 license, and all of our software is like that. That's the same license as Swift itself, as open source Swift. So we have a variety of components, as mentioned. Perfect itself, I see broken down into kind of these three different categories. We have the core, which contains, over here, perfect lib. You might find things like our JSON encoding, decoding, things like that, kind of foundational elements that all the other components are going to be using are in this core. Our threading package, which is built on pthreads. When we started on this project, GCD was not viable on Linux. It is now. But we still use our own implementation, which is very lightweight, and I think we're going to stick with that because it gives us flexibility. It's an abstraction layer, even over GCD, which is an abstraction layer over pthreads. So we're kind of similar, but we don't force anybody to use our threading package. If you're writing an app in Perfect, you might not even know, what's doing the threading, how or why. But on the flip side, we also don't handcuff you into, or prevent you, rather, from using GCD. So our threading package plays nice with GCD. You can be happy using GCD, or you can read our docs and learn what we offer here. The networking package, of course. We have a crypto package, and we use OpenSSL for all of our encryption needs. We don't use any custom implementations of any encryption algorithms, which is fun, but I see it as a little bit dangerous. And in addition to those four kind of core items, we also have our HTTP package. The first one just contains a lot of protocols, and the second one contains actual implementation of HTTP server. And the reason we did it like this is we also have fast CGI support, so we kind of abstract into the simple package, all of the elements that would be common if you're using an actual concrete HTTP server or some other sort of system like fast CGI, which you might think of kind of proxying requests. In addition, we have a whole slew of companion packages. A lot of them, initially, when we first started developing, were focused on just getting database support. all your basic standard, most popular databases we have support for. Support for SQLite also, which is good for kind of prototyping stuff. You wouldn't necessarily use it on the server as it is just a single user database. In addition, we have Storm, which is a companion project, which is an ORM, and it functions with MySQL, Postgres, Mongo, I believe. It might have a few others now, but it's kind of fixated on those core very popular databases. In addition, lots of projects for logging. We have curl support, authentication, websites. You can send notifications through HTTPS. And finally, lots of examples, lots of templates, tutorials, things like that. These are all on GitHub. I'll give you some links a little bit later. Let's talk about a little bit more of the nuts and bolts. So I talked about routing, and I'm going to describe that here. So a route is a combination of three things. You have your request method, and if you're not that familiar with the details of HTTP, it's not that important except to say that it's kind of for what are you doing when it gets something, when it posts something. In addition, we have a URI, which is just the part after the server name and the port that the client sends to the server. It's basically a file path. And then your code. So these get bundled up into what we call a route. So the server matches the request to the handler. So it does this by just looking at the data that you provided. Is the request a GET request? Well, we can write that's a GET. What's its URI? Does it match? Yes, it does. No, it doesn't. We have a few other features. You can put in wildcards or variables in the URIs as well. So these all get checked at this point. And when the server finds a match, the HTTP method matches, the URI matches, it's going to call your code. And so what it does there when it calls your code is it gives you a parsed HTTP request. You crunch on that, send out some stuff, and then the server takes it, builds it into an actual HTTP response, and sends it to the client. So here is a full example of the very simple Hello World type application. So as you can see, we import a few packages. We get the routes from the first perfect HTTP package, and then the concrete server itself lives in the second. So just starting at the top where we do our imports, I'm going to make a route object, give it a URI. So this one's just /hello. So when someone goes to the server, blah blah blah, .cn or whatever.com, and /hello, and you're going to get back this. So I mentioned the HTTP methods before. You see that's not in here. This route is going to trigger for any HTTP method at all. So you can either be very specific or generic in how you want to handle these things. I also mentioned how we have an asynchronous core, and you might notice how this particular code, we're talking about the closure here after the route, it's accepting a request and a response. You can hang on to this response object. You can return from this function we've provided. You can pass the response to a few other calls, add stuff to it, tweak it, and until you call completed, the request is still active. So again, this fits into the asynchronous model that we have. You can be doing asynchronous database calls, and as long as you hold on to the response object, you can always add stuff to it and then call completed. And what that does when you complete it, as I mentioned, it formulates the response, sends it to the client, and it might do additional things like keep the connection open for keep alive and things like that. But this is kind of how it goes. You put data in, you might set some headers, so you call completed, everything's done. And then down at the bottom, you can see that we're launching the HTTP server. We give it a name, we set the port, in this case it's just 8080, and then we give it a list of routes. So there's a few other objects. There's an actual routes object which bundles in a bunch of routes, but you can specify it in several different ways. In this case, I'm just doing an array of one item. Okay, this is a little more complicated. What we're doing is we're adding a route for /add user, and we're pulling out a variety of parameters. So this is how you would get the parameters from the request. Calling request param and then just giving it the name. Checking to make sure they were provided, is there optionals there. And if they aren't provided, we set the status code and then tell the response is completed and return and get out. Another example. So here's one where we're giving a user, or the URI is /user, and then in the curly brackets we have a name. So that's how you would add a variable. So I could say /user/Joe, for example. And down here, when we pull it out of the URI variables, we'll have that. And again, we can check and see it's mandatory or some sort of weird error, so we're going to null out. So what you'd like to do here is take that name, get the user. The user is able to be converted into JSON, so what we're doing is setting the response body to the JSON data eventually, and then handling errors in a variety of ways, and then completing. And you can see it starts with server much the same way. You can start multiple servers in one process. I do this often if I'm going to start, if I'm going to create a secure server, an SSL server. I'll also start up one on the regular port 80, so when someone hits it, they automatically get redirected to the secure server. So it's a very common task. So what we're doing here is just 4 different ways in which you might start one or more servers. In the first one, we give it our name, which is kind of for our reference, port, and then we give it a document. So what that server is going to do is just serve static files from the web root, images, static HTML file, what have you. The second one, we're starting 2 servers. One's going to serve static files, one's going to serve dynamic data from the routes that you've indicated. The third one here is showing kind of how you would do the same thing, but in more of a manual way. In the second part of the third example here, we're using a static files handler. So what you can do is have a server that's serving some dynamic content, some static content, and that's kind of how you would set that up. Final example just shows how easy it is to set up a secure server serving SSL. You just give the path to your certificate, make sure you're listening on the port that you want, and that's the way it goes. So pretty easy. All right, I'm going to cruise through what I've considered to be kind of best practices for using Swift on the server. Biggest thing is to test on Linux often. Test early, test often. And remember, there's no Cocoa, there's no UI kit. Don't try and use any of those things. Be careful with Foundation. Foundation on Linux is a brand new implementation. And there are still a lot of holes in it. Unfortunately, when they added all the functions for stubs, they put in the body fatal error. So, surprise, if you try to use something, your application will crash. But you don't want to have it on the server. And again, this just goes back to testing. Don't assume if you're going to use anything from Foundation on Linux. Don't assume that it works. Don't assume that it's named the way you think it should be named, and don't assume that it won't leak memory. There have been quite a few name changes. As you know, the NS prefix has been dropped from a lot of things, and it was dropped from some things on Linux, but not on Mac, and added back on Linux, and it's just a little bit sketchy at this point. It's all stuff that's settling down as we move forward. It goes back to one of my earlier points about sort of maturity. No Objective-C bridge. There's no deep class introspection in Swift on Linux. You can do introspection to get data bars, class bars and things, but you can't get as far as you could with Objective-C. And you could list methods that are supported and all this kind of stuff. And of course, there's no dynamic class modification, which you can do in Objective-C. Error is the default. Assume that every function that's getting called is getting called by somebody who's malicious, somebody who's attacking you. If it's up on the internet, you're going to get attacked. And all you have to do is just cruise through your access logs for a minute, and you'll see many strange requests. And you wonder, why are people trying to access these files on my server when I know they don't exist? They're trying to attack me. They're just running through their dictionaries of known exploits. So your server will get hit, for sure, with strange requests, people trying to hack you. So the goal is to never assume that the request is valid. Always be skeptical, I guess, in code. And as mentioned earlier in another talk, don't force them around. Don't do that. That will kill your server. Yeah, don't do it. Don't force them around. Security is very important on the internet. Usually when you set up a virtual machine, you're going to SSH access into the virtual machine. Make sure you secure those ports. A lot of the cloud providers allow you to set up firewall access. So if you're going to have SSH access to your server, make sure that it's only allowing traffic from you locally and not just anybody in general. And again, restrict the non-HTTP ports. So don't leave anything open. It's going to prevent a sort of attack vector. A good resource for security-related systems is called OWASP, which stands for Open Web Application Security Project. So there's lots of good tips there. They have lots of tips for doing penetration testing and just making sure you're not going to get hacked easily. If you store data, backups, always take backups. You can also do backups of that. I would recommend using a managed database system, which you already know a lot about databases. Most of these cloud providers have it. AWS calls it RDS, and they provide it for Postgres, MySQL, a variety of systems. So pick the database you want and look for one of these cloud providers that manage it for you, because it'll handle the basics of security and backups and that kind of stuff. Avoid storing dynamic data on the server. And the reason this is important is because it lets you take advantage of scalability, what's called horizontal scalability, which is where if you have one server and it's not able to handle your traffic, you add another one to it. And if that's not right, you add another one to it. And a lot of these cloud services, when you deploy to it, particularly the ones that run containers, you're automatically deploying it to more than one server. And they'll handle the redundancy, the load balancing for you. Again, you avoid storing dynamic data on the server because that data is not going to exist on your other instance. So you have one instance with this data, one instance without it. Doesn't make sense. This would be things like file uploads, if you do have a database on your server. For storing files, you can use shared file system, S3. There's a variety. All these cloud providers have their own kind of analogous systems. Do not share mutable data between threads. Structs are helpful for this because they're high value. Our threading package provides quite a few constructs for making sure that if you are going to share data, that you're doing it safely. We have your standard mutual exclusion logs. We have events. We also have a promise object, which is very simple but powerful to use. And as mentioned, you don't have to use our threading package. You can use what you're familiar with But this is built in, and it's kind of what our core uses. Load testing. So it's very important to remember that you're writing an app not just for one person, but for dozens, maybe hundreds of people to use at the same time. So even if you have a very simple, small site, always do load testing, because you're going to have people, if they're not trying to attack you, you have bots that come through and try and crawl your content for search engines and things like that. So even if it is a very simple site just for you or your friends or whatever, you're going to get some periods where you're going to have very high traffic, even if you're not advertising yourself. There's a few good tools for doing this kind of load testing. Siege, which I've heard good things about, but I haven't had a chance to use. Work and AB. Work is the one I'm most familiar with. Additionally, you can use kind of standalone clients, which are very handy. And this is compared to, say, opening up your web browser and typing in a request. And what these clients do, Postman, or two, is they allow you to explicitly say, what sort of headers I want to send, and they give you a good deal of control over the request. So you're not, say, having to use the browser. You can use this client, which is made specifically for testing your servers. Okay, almost done. There are several other server-side Swift frameworks, mentioning Katura and Vapor here. Those are two other popular systems. Katura is created by IBM. And if you recall back to some of the snippets I showed, Katura has a lot of similarities in how they do the request and response model. What's notable about Katura is they have very tight integration with IBM technology. It is an IBM project, so as you can guess, they're all about IBM stuff. Integration with Bluemix, Watson, all your stuff that IBM puts out. Vapor is another one. I would call it a little bit more high level. And what that means is that Perfect would be kind of closer to the operating system, whereas Vapor would have more levels of code on top of it. It might be better for beginners. As I mentioned before, all of these server-side Swift frameworks try and do the same thing, which is they take a request, run your code, spit out a response. So, what they're trying to do, what we're trying to do is all kind of the same thing, but we approach it in a little bit different manner. For Perfect, we try to approach it in a very, very performant and scalable way. Vapor's approach is kind of to make it more friendly, I think is a good way to put it. As such, there's kind of more constraints, whereas with Perfect, the way I see it is that there's a lot of freedom, and of course with the freedom you can hang yourself, but hopefully be careful out there. Resources. There are a few good articles written about performance and features. We perform better, if I say so myself. And so, there's good articles written by a nice individual there. Comparing server-side Swift to all the frameworks, Katura, Perfect, Zero as well, against Node.js, which is a very interesting article. He did the tests on Mac first, and then he went and updated it with the next test. So it really shows how well server-side Swift performs even against Node.js, which isn't bad. So very interesting articles, recommend those. This is where you get Swift on Linux at swift.org. You can join us on Slack. You can peruse our GitHub. There's all of our documentation, all of which is also available in Chinese. And we have a tool called Perfect Assistant, which if you're using, it's a Mac OS app, which we wrote. If you're using Swift Package Manager for any set of Swift server, or not, as long as you're using Swift Package Manager, you might want to check it out. It provides a lot of functionality. It keeps you from having to go to the command line so often, although it has a button, which is very nice, and will open the terminal there to your project. But all of your Swift management tasks, building, cleaning, managed dependencies, you can do through Perfect Assistant. We're currently doing beta testing version 2.0. In addition, if you are using server stuff, and not just package manager stuff, we provide a lot of deployment options. A couple at this point, Google Cloud and EC2. But we have plans for adding a variety of other servers, cloud providers as well. So that's worth checking out. Thank you.